That's what happens, I guess, with Macs. Not all the time. All right, so you should see here a PDF of the homework assignments with called a quiz, whatever. And again, you'll see the same sort of see if we can get the view. We'll get the thumbnails. If we can get 2 pages here. Oh, there we can. I just want to show you that here we have, with the Social Epidemiology Week, our 3rd mission. We can call it problem set 3, whatever. We start off with part 1, key statistical concepts. Right? This will have the R output, and then it will have just some questions, true or false questions, other kinds of output to interpret in sequence. Here's a write-in question that may or may not be actually in the other one, in the new one that the instructor posted. I apologize if that was different. Then we have part 2, which is data analysis in R. So there we are. So I'll try my quickest to review this as quickly as possible. I'm going to guess, since we're already 20 minutes in, I'm guessing 20 minutes afterwards. And I'm going to probably skip a few questions and focus on probably the most complex ones. That being said, if there's an issue that is of concern of yours or a concept, please interject. Tell me which one to explain. Maybe the multiplication rule, maybe some other aspects of probability, maybe questions where I can even bring up the PDF slides. Because I don't want to go just through score order, as it were. So in preparation of that, I'm actually pulling up the week 4 slides. Okay, so I have those up and ready. Okay, all right. So last week, I showed to all of you, look at that, I don't even have my video on. I apologize for that. Here I am. Good. You should be able to see me. Hold on. Where am I? Okay. Good. You should be able to see me. If you can't, please object. Okay. Okay, there you go. Here I am. I just wanted to show this to you. This is actually one of those cheat sheets that I mentioned. This is what I'm going to cover in the advanced R tutorials. There are about 4 or 5 of them. They're extremely useful. It's condensed information. There are sources out there for you, but one of the things I want to point out is this cheat sheet, which is actually a cheat sheet on using RStudio, which will be our first quote-unquote advanced R, which may not be too intimidating because we're using RStudio all the time. Just to let you know, it gives you an example of what the screen looks like, what the features are, and most notably, on the next page, it has the keyboard shortcuts. So especially for a Mac, which is useful for me because I've been a PC person for such a long time. Okay, just wanted to show that to you. Then we'll cover stuff like basic R, downloading and installing other kinds of data. Okay, that's it. Just wanted to show you what is sort of the emphasis there. All right, probability tables and relative risk. I'm going to try to focus a little bit more on this concept of relative risk. Why? Because if you haven't already noticed, there is something about relative risk, which is that it is ubiquitous. You will see this in the media all over the place. Right before section today, I was just Googling relative risk and just found it in a new study. Here's something right here. I'll just do another quick share. Just to show you that this is not an alien concept. Here's just, I don't know, some I just Googled this in Google News. Patients at increased risk for heart failure in cold weather. So here you have, it's probably observational data. If you recall, in the first week we talked about observational and other kinds of data, experimental data. I just wanted to highlight something here. They use some kind of more complex statistical model, but they showed, let's see, they talked about the increased risk of heart failure increasing as temperature drops. So this is notable because you don't have to have categorical risk exposure. Risk exposure can be like a dose dependence scenario, right? So in the way that, say, lead is a notable contaminant. The more exposure to lead, the increased risk to help your health. Or, for example, the more cigarettes you may smoke, the increased risk at those kinds of cancer or pulmonary disease you are exposed to. And in those cases, you're actually just interpreting a unit increase. How much does that increase your relative risk? So anyway, I just thought that was interesting. They showed for every 1 decrease of Celsius in temperature, in other words, the lower the temperature, the risk of heart failure increased by 0.7%, which means, and then they interpret it, right, which means a 10-degree drop in temperature over a week-long period, not common in Quebec, could result in a 7% increase in cardiovascular risk. Remember, we talk about percentages and proportions or probabilities much in the same way. So a 7% increase of a risk is actually a risk ratio of 1.07. That's how you would interpret it. So I just thought that was an interesting example, A, of how easy it is to find relative risk, even in contexts that are not exactly in our class. B, where the treatment, the exposure to the risk is not categorical, but it is actually numerical. And then the third one I'd have to say is the way that we talk about percentages and interpret, and the way we talk about percentages in journalistic accounts. It's not really a percent increase. It is a percent increase, but that's what essentially relative risk is. If we think about a value of 1 for a relative risk, means a 0% chance of an increase or decrease. Greater than 1, if you have say, so if you have 1.07, that would be 1 plus 0.07, which is translated to 7%. That's a 7% increase. So I know that's not a review of the homework, but I just think that's a good selling point for how crucial these constructs are. Let's see if we got this. No. I got another. Sorry, I got another one. Oh, here we are. There we go. Okay. So quiz instructions. We talked about this earlier as a social epidemiologist. What are the health risks of living in poverty, right? And we use that beautiful data set GSS. And I think you should be familiar with the flow of the instructions. I don't want to go through this too slowly. I just want to make sure I can get us to a one-page view. And I'll make this large enough so everyone can see it. Okay. So, oh shoot, I'm sorry. For some reason, we're getting to want to view a single page. Hide sidebar. Okay. Okay. If you can't see this, please just give me a chat and say the text is too small. Okay. So here we have the first bit of output, right? This is the logic that we have. Take a look at it. I wouldn't. This is why data analysis is good. You'll learn through experience. Variable names like depressed and poverty aren't that informative because does it mean you lack poverty? Does it mean you are not depressed? Is it continuous? Is it not? Well, you can. That's why sometimes I'll often triple read. I'll even kind of mouth to myself the information provided. Below is a contingency table of counts. That means these are people for two variables in the health GSS data set, depressed and poverty. Now we know a bit about the health, the GSS data set already from the introduction. And it says both of these variables are categorical with 2 levels each. So there we know a couple things, right? We have individuals in a survey, and these are counts, and they belong to one of 2 categories. And the labels of those categories, of those values to each two-level factor variable or 2-level categorical variable is informative, right? So here we have the what is it, the depressed column, right? On the, we'll say this is the y-axis, and on the x-axis we have poverty status. Okay, we want to know if poverty is associated with this. Okay, so, and we need to answer questions 1 through 5 for that. Pretty simple, right? I would say. Now, one thing you have to remember is what is a contingency table for 2 variables? It means that the value of each cell, if we can kind of draw boxes, this is not that clear here perhaps, but imagine this is like each one of these has a little box, these numbers has a box around it, and this is an Excel sheet. This is like a little box. I could draw it, but I don't want to spend time on that. Keep in mind that we took the group. We said we took two variables, and we just took, imagine we had everyone in the room. We split them up into 4 groups based on 2 responses. Are you poor or not poor? First response. Second response, are you depressed or not depressed? Okay, well, let's say I'm not depressed and not poor. I'm in the largest group. That'll be important. Now, the reason this is important is what is implied by the absence of this information, but by the fact that we're talking about a contingency table, is that the total number of poor people in the sample are in the columns here, right? So non-poors are here, poor are here, right? So each row is informative. In a way, you could think of this as a miniature data frame, right? You have, in a way, the reason I'm saying that is that you have columns and you have rows that each provide information on a matrix there. Okay, so what are the total number of poor people? That's 96 plus 52. This is where some guesswork comes in. If you don't know the answer, you can also use some logic here. You think it might be, well, I guess you could, right? This is where it gets tricky. We are adding up enough numbers, so if you're not too careful, you could get the wrong answer. So what is that? It's 96 plus 52. That's 148. That is the right answer right here. Okay. So there are some other answers that seem quite close. Nope, nope, nope. Although it's not as tricky as it could be. What is the total number of depressed people? Okay, here we got the rows. Same thing, same logic. You just add the rows. That's 99 plus 52. Right there, 151. Okay, so all we're showing, the pedagogical reason for this is how to interpret a 2x2 contingency table of counts. Did we answer all 5? I just want to make sure. Oh, there's a 5th one. How would we convert this contingency table to a probability table? Okay, remember probability is a probability table is defined by well, probabilities themselves are bound by 0 and 1. So that's the first thing we have to know. So think about what you would do beforehand before you consider what you would do. What I would do is I would divide each cell by the total sample size. And the reason I'm saying that is that because in our previous questions we showed that this is not a this is a contingency table, which is different than which shows the joint probabilities of belonging to both categories, which means that all of the cells add up to 1, as opposed to a contingent probability or a conditional probability. It's a little confusing. Conditional probability versus a contingency table. Contingency is about joint probabilities. The intersection, if we think about the Venn diagrams, the intersection of meeting two categories. So this requires, by the way, this is where I was getting at. This is actually, I think, the hardest part of these first 5 questions is reminding yourself that when there's no sample size, why can't I scroll up? I'm just going to go back to my mouse here. Come on. Okay. Okay. I'm just going to make sure I do a continuous scroll here. Okay, there we go. Remind yourself here, this is actually the first thing I was going to say, because it's a contingency table of counts for 2 variables, and we know that these are not conditional probabilities, that they're joint probabilities because it's a contingency table. All of those numbers should add up to 506. I could look at the answer key just to be sure, but that would be a typo. But that's the fact there. Let me just make sure. Yeah, 560, excuse me, because you're adding this, 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 and this. Okay, so that's actually the first thought in my head. I thought, oh, it's a contingency table. There's going to be a question about that involves the sample size. So that's how you do it. You take your probability of belonging in the group divided by everything. So, and that will create basically a value for each cell. It will transform each cell value to a decimal value, a proportion. And that's how we talk about it in terms of probability. Okay. I don't think it's more complicated there, except don't talk about it in terms of columns. Don't add the rows. Think of the cells. So mantra, take it to transform a 2x2 contingency table to a probability table. Cell divided by total sample size. Cell divided by total sample size. And this is also why I don't read the other answers, because it can be a mess, right? Because you might be able to find some alternative fuzzy math, we could say. Okay, as I said before, we go in score order. Use a musical term. We go in or a Broadway term. We had our first bit of evidence, you could say, first bit of output. Now we're going to interpret this. The question is, below is a probability table. Now we know what this is. Based on 2 variables in the health GSS dataset, depressed and poverty. Both of these are categorical variables with 2 levels each. Well, voici et voila, look at this. What did we just do? We're actually looking at what we would have done if we had asked you to estimate the value for each probability. So, right, because these are the same 2 variables, the same data set. All we do is transform it to probabilities. That being said, I really don't like having it to 4 decimal places. I think 2 is fine. So we have 18%. So just to review, the probability of being non-poor and depressed is 0.18. So you have an 18% chance of being in that group. You have a 56% chance of being in the non-depressed and non-poor group. You have a 17% chance of being in the poor and non-depressed group. And you have a 9% chance of being in the poor and non-depressed group. Now this is, I'm going to also add another important fact for you. This is different than relative risk. This doesn't really explain relative risk alone because these are joint probabilities. What this actually says, what question these data would answer is, if I were to randomly pluck a person from the sample, which group are they most likely to belong? Most likely they're going to be non-depressed and non-poor. Now if I were to pluck randomly from the sample, what's the least likely group in the sample? Well, 1 out of 10 times, or about 1 out of 10% of the time, or 9% of the time, I'll get a poor and depressed person just if I pluck randomly without replacements. You know, I just take a person out and put it back in. But that's a very different question, and it's very important because when we talk about relative risk, we can talk about how poverty increases the relative risk of something, but it also doesn't give but it also is informative to know what is the overall prevalence of depression or non-depression. And as a social epidemiologist, we have an interesting fact here. There are actually we have a greater probability in the United States of seeing non-poor depressed people. So not all poor people are depressed either. They have a greater likelihood for reasons that are well known, but we should also counter the stigma that poverty equals or determines depression, because many are not. So that's just an important point to make, I think, as well. And it's important for social epidemiology. We're always interested in prevalence too. So like a lot of the work I do is on drug use. I estimate the prevalence of opiate addiction, for example. That in of itself is important. We want to know what's out there, how much is it? This is what the CDC, the Center for Disease Control, does all the time. So that's just a bit of a fact there. Okay. And this is important for this idea of sample space, the list of possible outcomes. Well, here we have a very simple sample space, right? When we're predicting elections, and in the real world, it's not the case. As I told an ex-girlfriend of mine who took a stats course, I said, you're dealing with problem sets. This is what Harvard likes to call homework. I deal with problems. Problem sets are kind of nice and tidy because they do have a reason, a pedagogical reason. You only have a very small sample space with 4 outcomes. What are those? So there are 4 possible outcomes in total, but what are the list of possible outcomes for the variable depressed? Well, this and this, right? You just look across and see if you're depressed, what are the 2 outcomes? What is the sample space list of all possible outcomes for the variable poverty? You just look at poverty and look at those outcomes. And that's why you go to this answer right here. So this is another great example of concepts over precision in math. I really think as technology progresses, we're going to actually rely less and less on math. I've just heard the term data artisan instead of data scientist. You can make what you will of that. The point is, we want you to understand the idea that probability is, if you know anything about set theory or Venn diagrams, it's a branch of mathematics. considered at one point to be the basis of mathematics, but then it didn't really work out. But it's useful. But set theory essentially says, okay, here we have groups and we have intersections of groups. This is the Venn diagram stuff. Well, it's asking, well, what is the sample space? What is in the set of depressed outcomes? I apologize. Just looking at the answer, I realized I misinterpreted what sample space meant here for the variable depressed. I just want to make sure I got that right. Yeah, of course I did. So you don't actually look at the output up here. You should actually just think of the set of possible outcomes for the variable depressed as a set of possible responses. And that is within brackets, separated by commas. S is the total sample space. Looks like there, I actually gave you the wrong answer. I apologize. I answered the first question. See, I made a mistake, all right? If you don't make mistakes, you're not learning. Apparently, I apologize. Keep in mind, so let me repeat this. The sample set, the list of possible outcomes for a variable, is the range of possible responses. That's what it is. Hope that makes sense. That would never include numbers, by the way. Never include adding up those numbers. Okay. Right, so what would be, say, for a coin toss? What is the set of all possible? What is the sample space for a coin flip? It'd be S equals squiggly heads, comma, tails. One of two. Okay. Are these sample spaces valid? What do we mean by valid? Now, valid is a tricky term. You might think of validity in common language. We're going to use other words like bias or error is a term you're going to hear a lot that statisticians use differently. The answer is yes, it is valid. Valid in terms of probability. Why? Because it has two attributes. One is that they are mutually exclusive. And the second one is that they are collectively comprehensive. What a mouthful. Mutually exclusive, collectively comprehensive. Let me explain. So there we are. That's the yes. It's a little tricky because there are two no's. Sometimes it's good to see what the wrong answers would say. No, that's not true. And I'll tell you why. They're collectively exhaustive because we define them that way. S, by definition, is the set of all possible outcomes. It also happens to be the set of responses for each variable. If we wanted to say we could define S in any way. I don't want to make things too complex, but this is the flexibility of set theory, really. I mean, a set is just a collection of objects. It would be like, what's the famous one? I'm trying to think in set theory. All people on planet Earth, all living people, all Homo sapiens on planet Earth. That is a set. It's a collection of miscellaneous objects. Notice I said objects. They're not really, but that's anything is a set. It's just like an empty box defined by some parameter. You define the parameter, or the question does here. So it is collectively exhaustive because we define it that way. They're mutually exclusive because if you think about all people on planet Earth, you might look like somebody. I might look like the instructor, but that doesn't mean that you're the same thing. You're mutually exclusive. In other words, if you're one thing, then you're not the other. And in the logic of statistics and in variables, it means that you do not respond to yes to both categories. It would screw up your whole contingency table. Imagine if people could respond to both responses on the contingency table. You could say you're both poor and non-poor. Well, that's confusing. You're healthy and non-healthy. Well, how would that work? That being said, there are more complicated questionnaires. But think of the probability in terms of mutually exclusive events. So let's go back to that example in Quebec about temperature and having a heart attack. Your risk of a heart attack. You either get a heart attack or you don't. But you can't be both. Those are mutually exclusive. That would be for the variable, the outcome variable, the risk variable. Here we have depressed. That would be heart disease. It's collectively exhaustive because it's both two categories, and mutually exclusive because it's either one or the other. And that's extremely important for probability, right? A coin tosses heads or tails. Can't have both. Otherwise, I would definitely not play basketball with that person. Okay. What is the overall or marginal probability of being poor? Please round your answer to 2 decimal places. This is different because we've actually changed it to a multiple choice here. That being said, it's still good to have other kinds of answers. But what is the overall or marginal probability of being poor? Now, I want to just break down this idea of what does marginal mean. I kind of dislike the word. If you think about what marginal means, it can mean you're marginalized. Gosh, who hasn't felt marginalized? What it really means in this is that if we look at the 2x2 table here, and it's actually in the R code, marginal simply means, well, how could I explain it in an intuitive way? It means it's not central. It's derivative from the information in the contingency table. And I'll just show you up here. This is all the information you need in a 2x2 contingency table. If you want to add additional information, it's going to be redundant. You can add, I'll show you, I'll even draw right here. For example, this right here and this right here, these are both margins, basically, of something that is a 2x2 table. So here I have a little box here, right? These are the 4 cells, right? You have a 4-cell, basically 2x2 table. If you want to know what this and this adds up to, or what this and this adds up to, then you're adding something to the margins. Kind of like you have a margins on a book, marginalia, you know. There's there's a book, you write something right on the side. But the meat and potatoes is right here. That's what we mean there, which is different than if you take an economics class. It's also the reason why marginalization is considered a problem, because we don't want people to feel like they're, you know, on the outskirts of society. So that's the sociological reason for it. So think of margins as basically that. And again, it's redundant because we gave you all the information. So what is the overall or marginal probability of being depressed? Overall for depressed, right? Not overall for the full sample. So we just basically add this and this. It should be around 0.26, right? 1.18. Just add those 2 numbers up, and then you put your little number here. That's on the margins. Okay, made a little note. Marginal probability. Maybe I skipped that. Okay, maybe I got it mixed up. The marginal probability of being poor is this plus this. Yeah, that's 0.26. I'm sorry. And then the marginal probability of being depressed is, the other question asks, what is the overall or marginal probability of being depressed? All we're asking you to do is add up those cells, whether it's a row cell or a column cell. of one of the responses to each of the two variables in a 2x2 contingency. That'll be on the midterm and the final. Now then we have the probability of being poor and depressed. Well, what do you think that might be? Well, that's actually pretty simple here. Right there, it's the value of that one cell. We don't have to do any adding. It's the joint probability of both. So the probability of being depressed, we have to add up each of the disjoint probabilities, because we split everything into 4 groups. But if we're talking about joint probabilities, there you go. Much simpler. That's a kind of, I think, an interesting point, interesting arrangement, because here we have you adding up things, and then at the end of it, basically we give you an answer that is just plain as day. It's stuck right in there. Question 11, what is the complement of the overall or marginal probability of being poor? Okay. We all like complements, but that's with an I. This is one of the most commonly misspelled words in the English language. Don't worry about it. So complement I means you've heard something very nice today. And I hope everyone gets a compliment every day. A complement, C-O-M-P-L-E-M-E-N-T, is different. It's also something that you might hear in common parlance. Now, of course, we covered this in lectures. It's important to emphasize. You could say, I don't know, maybe I'm just being too academic or too statistical. I would probably use this word. I don't know if most people do, to be honest. But the complement in statistics is the probability of, what is it? I'm going to try not to use jargon. If you have the probability of A, then you want the probability of not A. That's the complement of something. So, for example, if the probability of, say, a heart attack is 7%, as we saw, let's just keep that, even though that was a more complex example, the complement would be 1 minus 0.07. So the complement is also logically known as the contrapositive of that probability, which is a little confusing, I think. It's not always intuitive. So you have it's basically, and of course I think this is where
it's 21 hours.
I'm sorry, this is not my butler. This is actually my Mac having more control than me. I apologize. Apparently it likes to tell me what time it is. That was funny. Okay, well, he won't speak again. All right. Did it in British time too. All right, well, anyway, so what is the complement or the overall marginal probability of being poor? It is 1 minus the probability of being poor. And of course, this is where it helps to build on previous answers. Remember, you don't have to add up the probability of being poor. You could just take the previous answer. Now, here's where it gets complicated. I call it the propagation of error. You make one mistake, it might tumble into other errors. This happens all the time. So just FYI, maybe if you have the time, I would try to just calculate it by yourself. So what would you do? You would basically add up. Hold on for a second. Yeah, you would take 1 minus 0.26, because the question here is, what is the complement? Question 10. Sorry, question 11. Complement of being poor. I'm going to scroll up and just show you. Poor, remember, you add this, that's 0.26. That's the marginal probability of being poor. The complement of that is 1 minus 0.26. So that is 0.74 or so, 0.7357, something like this. But 75%, 0.74, that's what it is. Does that make sense, I hope, the idea of the complements? Yeah, okay. I would go to the sections where we have Venn diagrams that really illustrate that clearly, I think. The addition rule using a probability table. Okay, so there we gave you probabilities. We could actually, use the addition rule to figure out probabilities. Now keep in mind a probability table here. What do we know about a probability table, given that what we're providing to you is a legitimate probability table, which is what we're going to do because I don't want to hurt my reputation by calling something a probability table where it is not mutually exclusive or what did I say? Comprehensively exhaustive, right? It has to be comprehensive and it has to be mutually exclusive. In other words, the sample space, all of these probabilities have to add up to 1, and also one belonging to one subset or one category, one set, you could actually say, in the sample space. You can only belong to one sample space. Let me put it in clearer terms. You only belong to one cell within the contingency table. Keep that in mind. When we say probability table, we're talking about disjoint probabilities. We're talking about variables that are mutually exclusive and that are comprehensive. And of course, it's the same. It's actually what we've seen before, right? It should be identical. Let's take a look. So what's the difference? We just call it a probability table, and we're going to ask you different questions. What is the joint probability of being depressed and being poor? Well, that's an interesting question. Well, you can just look at being depressed and being poor. And there it is. Notice again, this is the same answer that you've had in an earlier question. The difference is the language, the framing, and the thinking of how to figure out the problem. This is what probability is. Probability is a way of thinking. It's a mental framework. It is not just about stats. It is actually thinking and applying those stats. We got machines to do the mechanical work. It still helps to program, trust me. But when we talk about joint probability, if you know anything about SQL, that's kind of a database management system. I always think of SQL when I think of joint probabilities. You're thinking about the intersection of a row and a column. What do you find there? I'm not that big on database management, but there you go. What is the probability of being depressed or poor or both? Okay. Notice that we're using or here to refer to the probability of being depressed, being poor, or being depressed and poor. Okay. Here's another tricky example. When we talk about or, we're not talking about it perhaps in the normal way. Would you like to go to McDonald's or Burger King? We're not asking. If I ask my girlfriend this, she'll probably say no. I don't know. But she's not. But she never would expect me to say or to include both. I use that example because it's so bizarre. It's kind of memorable that you sound pretty silly if you ask someone, or if you want A or B, but you also consider both of those possibilities as an answer to or. That's how I actually remember or within the logic of probability or set theory more broadly, or mathematics more broadly, right? So what does that mean then? And we're giving you a big hint here. We basically have the probability of A or B, which equals the probability of A, probability of B, minus the joint probability of A and B, right? Because we want to know whether it's purely A or purely B. We don't want those mixed up. It's a very precise way of thinking. It's clear with Venn diagrams, but just keep that in mind. That's another bit of language here. Please round your answer to 2 decimal places. So this is where I would write down the answers that this is where I'd write down the bits of information. You want to know the probability of being depressed, the probability of being poor, and then the joint probability of being depressed and poor. You want to add probability of being depressed, probability of being poor, and then subtract that probability of being depressed and poor. So in this case, it would be, hold on for a second. I think we answered those questions earlier, right? We answered probability of being depressed and poor. We got that here from question 10. So there we have the A and B. What is the probability of being depressed? We have that. That would be the probability of A. And then from question 8, we have the probability of being poor. So this is also something that you'll sometimes see in these exams. You don't have to construct things de novo, ab ovo, as they might say in literature theory, of the egg from nothing. You can actually borrow and build on your previous information. And this is what we do in stats. Of course, this is why we always have people double checking. This is why I never like doing work by myself. But it's good. That's the healthy kind of skepticism. We gave you those 3 values. You just have to know that you have to add, what is it, 0.26 plus 0.26 minus the joint probability, which we've reviewed twice, which is around 0.09. So 56 minus 9 is 55, is a 45. And that is the probability of being depressed or poor, or both. Sorry, yeah, the probability of being depressed or poor. But not excluding the both there. And that's the addition rule of probability. And that's actually quite important. I mean, if you think about probability, we talk about items being mutually exclusive. If you're talking about A or B, you can't talk about the probability of A or B if they're mutually inclusive. So you want to exclude that joint probability. Okay, that'll be on the exam. The joint probability of being depressed and poor is question 12. The joint probability of being depressed and being poor. Wait, I'm sorry. I was did that already, right? Okay. Why do we subtract the joint probability when of two events using the addition rule? Any kind of answer would be correct, but the point is that we would count the joint probability twice in our calculation, because remember, each one of those A and B are both joint probabilities, so we don't want to add joint probabilities plus the concurrence, because they can occur at the same time. Then it's no longer an OR. So that's probably actually even the more intelligent way of thinking about it. But I think because we use OR in a different context, in a more fuzzy way, perhaps you can take the logical approach, which is also the fact that when you have joint probabilities defined by the intersection of 2 categories, by definition, when you add them, you're also adding the overlap of that joint probability. And we want to make sure that we have, we subtract that overlap, that joint probability of both. So yeah, we want to subtract the fact that they can occur at the same time. Then it's no longer OR. Okay. Let's see. Unfortunately, you don't have to answer that because I think that's a little more difficult. Suppose a researcher wanted to use the joint probability of being depressed and being poor as a measure of social vulnerability. Okay, social vulnerability is a quite common term How might this measure be misleading? What are the benefits of this measure compared to an overall probability of being poor? Okay, so we talk about the joint probability of being poor and being depressed. Again, this is where you can build on previous information. The joint probability of being poor and being depressed is overall small because it compares poor and depressed to the overall sample, to the overall population, which includes the non-poor. So it's going to look small. Okay, well, that's why it would be misleading. It doesn't really show the relative risk or the conditional probability of being depressed compared to being non-depressed. Because that also accounts for sample size. There are more non-poor people than poor people. So we want to scale, we want to have a conditional probability that says, okay, if we look at just poor people in the sample and the non-poor people in the sample, of those two groups, when we look at conditional probability, what's your highest conditional probability? Here's a really good example of that, I think. When you look at, say, police brutality in the United States, which is a big issue for a lot of social movements, Black Lives Matter, the concern among Black Lives Matter activists is the disproportionate abuse or maltreatment by police toward people of African American descent, or people who are non-white, really. Now, that's a small percentage of the population. About 12 or 14% of Americans are define themselves as Black or African American. So you might have, if you look at the overall rates of police brutality, because there are more white Americans than Black Americans, you might see a greater number of police brutality cases among white Americans. And that's important, of course. But it also obscures the fact that if you're Black, you are disproportionately likely. In other words, your relative risk is much more likely. Your experience of police brutality is much more likely. So that's a key issue and fundamental to understanding the complexity behind a lot of political debates. I think when we talk about political things and we talk about even a lot of science, a lot of social science, it's good to, for me even, look at the numbers, look at it from different perspectives, look at things from different angles. A strategy that I've often heard is figure out the best argument of your opponents, adopt that, and then see what that looks like, and see what you can argue against, and then see what you learn from that. I think that's what statistics should help you to do, and I would hope it would overcome any cynicism that a lot of people have towards statistics. Journalists, for instance, oh, you can lie with stats. You can lie with stats, but it's easier to lie without. Statistics show you the complexity, that reality of that actual reality in which we live. So there are pluses and minuses to a lot of different things. So it could be misleading to look at just being poor as a measure of and depressed if you're comparing it to the full population, because the poor population is small. What are the benefits of comparing this measure, poor and depressed, to an overall probability of being poor? That's exactly what I said. In other words, if you look at just among poor people, you add up that column, and then you look at the proportion of poor people versus the proportion of non-poor people, you'll see that you're more likely to be depressed if you're poor. And the relative risk is the ratio of depression rates by exposure status, right? Whether you're poor or not poor. So that's also crucial. It conveys also, I think, perhaps even more relevant information, because you're not comparing apples and oranges. You're basically saying, well, no, I'm not going to go there. I think there are benefits and disadvantages to comparing different ways of looking at the complex social universe. Best approach, multiple approaches. Okay. All right. Now we're going to talk about the addition rule. We're talking about the multiplication rule. Okay, I'm already over time. That's okay. I prefer to talk more slowly because I think this is the more difficult week. Probably the most, actually. Okay, so we have the addition rule, right? It's to talk about the probability. When you look at a contingency table, you look at the probability of one event or the other, and you subtract their joint probability because, the probability of both together, because they're joint probabilities by definition. When we talk about or, we're talking about something or nothing, or one thing, probability of one event or the other event, and we want them to be mutually exclusive. The multiplication rule is, well, I just want to make sure we're looking at the right data here. Okay. Yep, okay, so here we have the same probability table. So look how much you can do with the same amount of data. What is the unconditional probability of being depressed? Oh, well, this is great. This is language. Remember I said there's a lot about language, the use of language, the specificity. What is an unconditional probability of being depressed? Well, that's what we talked about before. It's the marginal probability. In other words, out of everybody, what's the probability of being poor? Well, we don't have that information here. If we did a tally function of just the variable poverty, then we would just split the group sample into two proportions, right? We could do that. But since we're stuck with this amount of data, which is going to be common if you work anywhere in government, for instance, they're going to give you reports and you're going to have to reinterpret them, then an unconditional probability is simply the marginal probability. So what is that here? And I hope you understand what I mean by unconditional. It means it's no longer joint. It means the probability of both categories. So here, all we do is it's the marginal probability. So it's 0.27. We just add them. Is it being depressed? Yeah, the being depressed. We just add this cell here and this cell here. And to interpret that, I'm just going to give you a little extra. What does that mean? It means out of the full sample, 27% report being depressed. That's a big proportion, right? That's important for social epidemiology. I think you could publish that. I've seen papers published that will talk about, here's the population prevalence of important disease or malady, right? 26.7%. 1 out of 4, that's pretty large. Okay, especially since I think mental health coverage is not really, it's pretty lacking for many people. Okay, so keep in mind the lesson there that we're trying to teach you. You got marginal probabilities, you got unconditional probabilities. And yeah, that's all that we need to know there. Unconditional just means, it doesn't matter on anything else. We're no intersections here. Just we want to know what's going on for one variable. What is the probability of being depressed given that a person is living in poverty? All right. Look at this phraseology. What is the probability of whatever given whatever else we want to know that splits the sample? So we could say, what is the probability of being depressed given that you're female? What's the probability of being depressed if you are over the age of 60? What's the probability of being depressed if you are a registered Republican? Right? What I'm going to point out is it doesn't really matter what this given thing is, except that it is what defines you into the exposure group, I guess you could say, is what defines the sample. And this is a condition. And the first thought in your brain should be, okay, we're not looking at joint probabilities, we're looking at conditional probabilities, right? Think of that vertical bar in the syntax. Given that we know this, okay, what's the probability? So how do we do that? Well, shoot, we actually can't do our own stats. We actually have a table of disjoint probabilities. It uses the plus operator in the syntax. So someone wrote the wrong code. We are stuck with the table. What are we going to do? Well, we can use the multiplication rule. We can basically figure out the probability of this is why we need to do this. Hold on for a second. First, we need to know the probability of being depressed, and also the probability of being in poverty. So okay, and how do we figure that out? Well, we just basically take the probability of the exposure within that conditional subgroup. Remember last time I talked about how each column adds to 1. You're splitting things into groups. So what you're going to do is you're going to average. You're going to add up all the disjoint probabilities to define the risk group, the sample space, not the sample space, but the risk group, the exposure group. And you're going to take that as the denominator, I think, the numerator. The denominator is on top of the fraction. You're going to put the probability of being depressed, given that you're in poverty. We know that. That's the joint probability. We keep running into that. So what our answer is going to be 0.09 divided by the two probabilities that tell us the proportion who live in poverty. Well, how do we know what's the proportion of people who live in poverty in the sample space? Look at this. Less work for you. You're going to see this time and again. This is how you're going to speed through the exam. On question 16, we just gave you that answer. We gave you the answer of the probability of being depressed, right? Which is about 0.26. So it's going to be 0.09, which is the joint probability of being depressed and poor, divided by the probability of being poor, which we just answered before. So there you go. Okay. What is the probability of being depressed given a person is not living in poverty? Okay. Let's see if I, okay. So this is not going to be too hard. Remember, what is it? Okay, I just want to review the question myself. Hold on for a second. The first thing I do, and this is kind of the annoying thing about this, is just look back at the table if you're not taking notes like I am. Keep in mind that you have your numbers intact. And I would typically write things out, but my penmanship is so bad here. So keep in mind, we're still doing a conditional probability, right? The conditional probability, given that you're not living in poverty. So we just want to know if you're depressed, given that you're not in poverty, you just take 0.17 divided by this column right here, right? 0.1768 plus 0.589. So given that you're non-poor, we estimate that probability. It's about 75% because we know that the probability of being poor was about 26%. Yeah, okay, I'm just looking at the math to make sure I'm correct on that. And so you take that ratio. So you take 0.1, you take this divided by both values divided in the column. This is a fraction. What's that? That's about 0.24. Okay? So we have a value. Oh, now I'll finally write this down because this is going to be important. We just estimated two conditional probabilities using nothing except a probability table. So this is important for us to remember, is that you don't have to have conditional probabilities estimated. You can have just a probability table and add things up to find out conditional probabilities, marginal probabilities, joint probabilities, complements of probabilities. Don't worry, this will be recorded and you'll see it again. But keep in mind, So the probability of being non-poor, sorry, being depressed given that you're non-poor is 0.351. Well, I'll just do that. I'll just try to put underneath each column. The reason I'm putting this here is because I think this is actually kind of important to remember. And then I'll put out another text here. And this right here is, sorry, 0.240. Notice I got this backwards, by the way. Oh, I'm sorry, I didn't notice the questions. Please. All right. I also love to use R as a fancy calculator. This is how I'd often do it. And I'm sorry if this is gonna be an overlong section, but I won't apologize. I think this is to your benefits. And you can always just skip ahead. I'm gonna do a new share. Thank you, Walter. And I'm gonna share with you my R Studio screen. Okay. Yeah, we still have the data here. I don't have the code. I don't really care. Mainly because we can assign objects here, right? We can say the probability. Okay, well, everyone's all right. It's okay not to do R or to take a little bit longer to explain some of these concepts. I'm not sure. In any case, so the probability. So we can say conditional probability. We can assign it as joint prob divided by unconditional prob. Make sure, yeah. Doesn't want that object defined. Oh, because I have to define each object independently. Anyway, the point is you can actually do a lot of mathematics here. So for example, if you want to know the probability of being depressed, given that you're living in poverty, you would just basically add up the probability of being depressed and poor. So this is poor. You're going to assign it as 0.09 plus 0.17. So there you see 0.26. That's the unconditional probability right there. It's right there. And I just added those two cells on the right. Then you're going to take the probability of being, the joint probability of being depressed and poor. And you're going to assign that to that value, 0.09. And then, quite simply, you're going to take, you're going to define as, I don't care, we don't even have to, we'll define answer as, you can say conditional probability is the joint probability of this divided by the unconditional probability of all poor people in the sample. Answer, you're going to print it here, 0.346. Okay, so I did quite a bit of, this is the problem with rounding. You don't round to 4 decimal places. Instead of getting 0.351, you get 0.46. But still, look, 0.35. So that's the probability when you pour. The point is you can actually use R for that. I do have a tutorial. R is a fancy calculator. I will show that and post that. That's just a great way, I think, that I hope it is useful for clarifying some things. That's how I do stuff. I don't use Texas Instruments anymore. Okay, let's go back to the answer sheets. The reason I don't do too much of that is I want to think about it in terms of words. I want to think about it in terms of concepts. But all it was, I added this cell, and divided by that other one. Okay, so here we go. What is the probability of being depressed given a person is not living in poverty? We already calculated that. What is the relative risk? Oh, well, we already knew that from the previous two answers. In fact, that's what we did in the problem set too. And I thought I wrote those down. If not, remember the answer here, this was 0.35. So you have a probability of 35% of poor people are depressed. That's how you say it. The conditional probability if you're non-poor is 24%. So 24% of people who are non-poor are depressed. Well, what's the relative? So that gives you the absolute prevalence for each risk, the exposure group, which is poverty, or the absence, the complement of exposure, right? The absence of exposure. So here we have 35% and 24%, both pretty high, I'd say, right? This is now where we go to the language of relative risk. Then you just divide 0.35. I hope I'm right. Yeah, over 0.24. Why do I always doubt myself? I don't know. And that's 1.46. So the relative risk of 0.146, and that is the ratio of the conditional probability in the exposure group divided by the conditional probability in the non-exposure group. Those conditional probabilities also show important prevalences. Whenever I look at relative risk, I always want to know those conditional probabilities, because you could have, as that's what I was trying to show last week, you could have very low conditional probabilities, but a very high relative risk ratio. Here you see something interesting. You see that Americans are pretty depressed, even if you're not poor. 24% is still high, I would think, if you're not poor. But if you're poor, it's still higher, but not so terrifically higher than if you're non-poor. And we know that from the relative risk statistic. And the way we'd say it, if we had a journalist write it up, you would say, okay, Dr. Fossey wrote an article on poverty and health and found that the poor are 46% more likely to be poor than non-poor. They probably won't report the conditional probabilities, they don't have space, but they'll tell the main story. Poverty increases your risk of depression. Okay, and then they quote me about policy and what we should do. And then that's the end of the story. But that's what you're missing. Okay, any other questions, I guess? All right, data analysis, we sort of did that before. Are there any other questions regarding that? I think we answered all the questions for the data analysis, but yeah, that's relative risk for you. All right, well, if there are no other questions, thank you very much. Thank you for your feedback. I would say Excel sheets are great, especially if you know how to work them. I'm not so great at Excel, but many people are. I'm just learning. A good old-fashioned calculator is just fine. Oh, thank you. I know, right. I apologize. Maybe I'll share the desktop. The reality is, if I were to take this test, be taking this test, I probably would be, what would I be doing? I would actually be writing probably everything on paper and using a calculator, to be honest. I think that's faster than what I was typing out. But if I want reproducible code, which happens quite a bit when you have to do stuff, that's more important. But for me, I always like, I'm old-fashioned, and the math you have is not going to be too complex. Simple calculator will work. And I do need arithmetic, but it's more than just arithmetic. My ex-father-in-law was one of the more famous mathematicians. His wife did his calculated the tip for him, because for him, math is not about arithmetic, and I think that's an important point. It's about a lot of spatial reasoning, a lot of its creativity. If you like Sudoku, he likened it quite a bit to Sudoku. Anyway, if you've read his book on partial differential equations, you might have heard of him, because he had sort of the graduate textbook on it. But you also made a really good point, which is that if the student is not learning, it's the instructor's fault. So please, if you have any other questions. So someone's asking about the mission. Hold on for a second. I'll answer that because I think it's a bit specific. But great question. Hold on for a second. But anyway, that's it for this, and I'll just to give you a sort of a preparation for next week. I don't think it'll be as difficult. I think it'll be fun. It's going to be correlations. And correlations you're going to see everywhere. And I'm going to show you a couple fun sites that I'm going to put on the discussion board. One is called Guess That Correlation. Fun. The other is spurious correlations. You can find tons of spurious correlations. And the main fact you're going to find is correlation is not causation. And we'll talk about that. And that's also why you need variance. But that's where you get into real statistics. The other stuff on online, be clear about where to find things. That's crucial. Okay, thank you very much. And I'll answer that other question. Thank you. Okay, I stopped sharing, so we're not recording. So, Amanda, you had a question. I have been handling, okay, yeah. I'm going to ask the course instructor to do that. Here's the deal, and this is, again, part of the problems with I think, a lot of things when you don't program them yourself. We use we use like the Apple. Thank you, Walter. We use the Apple version. By the way, Walter, I know you had mentioned before your interest in advanced R. If you have something specific, and this goes to the rest of you, tell me. Otherwise I'm going to go through these cheat sheets, and some of you might find that to be rote, but I think they're pretty rad. Print them out in color and glossy color. It's just great stuff. And by the way, it's also reliable. You're not going to find some janky code that was written on GitHub by someone like me who just don't design airplane. Do not design your airplane wings on those people. The people who are writing this stuff, many of them are like Hadley Wickham. They basically developed R. So that's important to know. Yes, they're the most useful functions and the most useful libraries. They are the ones that we trust. That being said, go ahead and try anything else you want. Where to get it? I showed it to you last week. I haven't posted that video. I'm also gonna. I also just created a help video that shows you the 3 ways to get help. I'm just transferring that from YouTube to the Canvas website, so people, because people are shutting down the internet around the world, and I want to make sure that information is free, and YouTube is not available everywhere. But yeah, where to get it? But you know, I'm just going to show you right now. I'm sorry, Amanda. Amanda, I will look at that before Luis. I just want to say, Amanda, I like your idea, turning it on and off again. Here's the problem with when we talk about grading and code books. I don't know of a way to do that. This is why Canvas is a little bit like a Mac. It's as a tech guy said, it's sort of like there's a lot of rules and regulations, but it's very flexible, especially for programming in Python. But it also is a little constrictive in some ways. Like it'll tell me what time it is in a British voice. Sorry about that. So I'll see if that's possible. It may not, but you can still review it. I'm not sure. Is there an advantage to you want to retake the quiz? I mean, you could just print it out. What's the advantage of keeping it indefinitely open? And others can chime in too. I'm just curious. I wouldn't know because actually my strategy would be to just review the review sessions and then also print it out. Yeah, go ahead, please.
So my question is, when you have the missions open, they can stay open for a longer period of time, and so it'll save automatically. You can come back to
I'm not hearing you a little bit, but I'm turning up my volume.
Okay, how about now? Is it better?
Yeah, yeah.
So my question is, you're able to return to the missions and it automatically saves. But
Ah,
the exam, I'm wondering if there's a certain period of time in which we have to complete the exam, or if it's going to be, are we allowed to use all of our notes and everything, or is it going to be like a certain period of time that you need to have it completed by?
okay. Yeah, I wasn't that clear. I guess I was using the incorrect metaphor. First of all, remember we have three kinds of problem sets, right? We have the quizzes, right, which are basically kind of our tech version of participation, right? Which is like complete them, you get them. Then we have the homeworks, which are graded, right? And those have a definite endpoints. I thought you were asking about that. Then we have the midterm exam and the final exam. Are you asking about the midterm and the final exam, just to be clear, Amanda?
Yeah, I am.
Okay, so the midterm and the final exam, you have an allotted number of days in which to begin and end it. Sorry, you have let's say I don't remember the exact number of days. I think it's 3. You have 3 calendar days. I hope we can give you more. I'm not sure, but what it was. Let's just say 3, just for hypothetical sake. You have 3 days in which to complete the exam. Okay. So that means that if you start the exam at any point within that 3-day period, then you're okay. But once you start the exam, then you have to finish in the allotted time. So you do not have 3 days to finish the exam. You have a 3-day window to start the exam. Does that make sense? Okay. Walter, you said yes. I'm hoping, Amanda, it makes sense to you. Yeah, similar to previous exams. It's our version of a blue book exam where we have you in that lecture hall. Everyone walks in nervously. You have you have a proctor for the exam, and then open your books. You may begin, pass them in. That's essentially the digital analog. Yeah, there you go. So that's why it's sort of like I almost want to say a rental in a way, because you can buy. I'll give you just an example. You can rent a movie on YouTube. You have to use it within a month. Once you activate or start the movie that you rented, then you have to finish it within 24 hours or it expires. Okay, so that's why I'm also talking a little bit about strategy, if you notice. Like I'm saying, oh, look, we already gave you the answer. You can build off that earlier answer as long as you're careful about that. I'm trying to get you thinking about building on previous knowledge rather than starting all over again with each one, taking the easier route than the harder route. And that's why we also have the practice exam. And that's when I make it a Zen moment. Light some candles, maybe play music if you like that. Be comfortable, be cool, get distractions away, be happy, be confident. And there's this whole thing called the imposter syndrome that is ubiquitous. One of my mentors, a social psychologist, talks about this. Happens to the best of us, trust me. Right? Okay. And all that means is essentially a loss of confidence when, I don't know, you don't find anything statistically significant for 6 months and everyone else has won Nobel Prizes. It happens at every level. So that has nothing to do with knowledge. Okay, thank you for everyone. And yes. So James just sent this. It is the yeah, right. This is the data science field. Yeah, and most of you are graduate students. I'm not sure if you've all taken the GRE. I'm not sure what subject they'd recommend, but yeah, I think it's great. I mean, look, I love the courses, especially the advanced ones. What I'd like to see more in the data science program that I'm hoping to contribute is to jump from here to there. There's a big difference between stats and machine learning. There's even some conflict there. But we can talk about that later.
Are those classes online or partially online or mainly all on campus?
Most of them are online through the Extension School. Some of them, I think, are online. Machine learning equals, yes, of course. Yeah, my goal actually, Walter, is to, look, there are stats wars. Learn Python and R, you're golden, you're good. That being said, if you notice what we're teaching in section, and if you look at the homework assignments, yeah, there's some R there. But the actual modules in the lectures it's about the content, because languages come and go. The stats theory stays. So I would love to provide this course in R as well. Integrate Python. Sorry, in Python. That being said, just learn both. You'll be good. In the sequence course I'm going to propose, I'll be integrating R and Python. That's all you need. So, people like the Python nowadays, but I like it too. But no, R is beautiful. The course that I'm proposing to teach would be the next calendar year. It would be a sort of a follow-up on this. It follows up on sort of regression plus, I would hope, machine learning. Because I know it sucks now. It gets more fun the farther down you go. It gets crazier and crazier. Really cool stuff. It'd be like some version of Stat 150. But it'd be the sort of the sequel to this. Yeah, because I don't want you to take this class and then have to learn SPSS. No offense to people who learn SPSS. I've learned it. I know it's good. It's an important language. But trust me, Mark Zuckerberg is not looking for SPSS users. He's looking for Pythonistas or R freaks. Anyway, okay. So thanks a lot, everyone. And by the way, machine learning is not just Python. Stats is Python. And machine learning is also in R. Machine learning is also in some of your regular stats packages, which shocked me a little bit. Okay. Yeah. And I don't know. I wish I could talk about those differences between stats and machine learning. But anyway, that's it. I don't want to take up more time. Any other questions? All right, thanks. Good night, guys. Thank you. My girlfriend's out at the other door. So she wants to learn R. She's a neuroscientist, wants to learn R. Okay, but I'm telling her to learn Python. Okay. Good night, guys. Good. I'm glad, Luis. I'm glad it's fun. Okay. Thank you, guys. Bye, bye, everyone. Guys and girls. Sorry.